Hello everyone, I'm an engineer from Intel. My name is Liu Changpeng. This is my colleague Liu Xiaodongl. So we have achieved SPDK Vhost fuse target. I'm going to present the slides. Before we do these things, we want to tell you why do you want to create an vhost fuse target. If you are listening to the morning session, or if you have used a container or VM for 9pfs, maybe you will be more familiar. Actually, in the beginning, if you want to use the user state, we're using 9p. We're also discussing about the disadvantages of 9p. We have also talked about whatever fs. So then we shift to fuse. We have already do something, and we have also done a simple compatibility with fuse target. That's why I want to demonstrate that to you about what we have achieved. Before we start with this topic, I want to tell you what is SPDK. Actually, it's a set of libraries. At the bottom is the QEMU, and then these are the blocks and storage layers. And I want to highlight about what we're doing is up to 2 million packets a call. So we already reached tens of millions calls levels. On our webpage, we have described about what are the things we have done, and we also have a comparison with the new technology. This is the architecture of SPDK. From the bottom layer, we have NME driven, and also we have quick data and copy engine. And based on that, we have storage services, and we have block device drive. A larger volume can also be used for block management. We also have decrypto. We also have OCF cache. And this is the open channel FTIL. This is compression engine. Above that, we have storage protocols, NVMe target. In the previous topic, we have already talked about that. In the vhost, we have vhost dynamic vhost host, and today we're talking about vhost fuse target. And this is a user state implementation, and we also have Blobstore, which is a block management distributor. This one is about unified SPDK vhost user target. We can look at this. We support vhost user block. We support Warehouse Gossip. And similarly, we support vhost VME. So we can use VME protocol to decipher. And this is about the vhost fuse target. So we can build on common vhost user library. If we don't know about vhost, actually what how is defined in spec. Vhost is a time limit. Basically, there are two experiments. kernel and in kernel.
然后还有一种是 Vhost use，
And also Vhost
用
use
实现的这种 Vhost 的这种 target。然后最
for the
重要的
Vhost
一个优
target.
势 for Vhost user 呢，
The
其实就是
biggest advantage of
消除这个
Vhost is
MIO 的
that it
access，
eliminates
就是提交信息
MNIO
这个
access
后端的时候，
for submission with
然后
polling mechanism.
是减少这个 MIO 的 access 主要的实现的那个方式是
And the way
使
to
用
achieve that
polling 形式。
is to use the polling mechanism.
那抛出来这个问题呢，那我们就说，如果是说 share 一个
If we're
file，
sharing
就是
a
从 guest
file
到那个 host
from
那边，
guest to
咱们目
host,
前有的一个方案是
our existing
FS， 对吧？然后
protocol is
9P FS 呢，目前
9P-fs. There are also two ways to achieve that.
第二种像是
I have listed here.
第一种是这一
The
个
first one
叫
is this.
Virtio-fs， 这个是
Without
QEMU
the
里面实现的，也就是说，你如
9P-fs,
果是使用那个 QEMU 的这种
if you use QEMU
QEMU process， 然后
process,
这个 RO 的这个处理，那
our
就是在
processing
QEMU 本身这个
will be
处理掉
within
的
the QEMU.
有的 Virtio-9P。
So this is Virtio 9P, and
但是这个 Vhost-9P
there is also Vhost 9P. I didn't add user here because this is a kernel solution.
然后这个 kernel 的方案也没有
For the kernel solution, there is also upstream minimal strong.
做的一个 Vhost 9P 的一个
So
kernel，
this is the
然后其实也
Vhost
是之前
9P
8.0使用
kernel.
的一个kernel 方案。那我们看它的后端的实现。
Now let's look at the back end.
那个前端的话呢，
For the front end, it's the same. We have 9P kernel, we have 9P driver. For the back end,
通过 Virtio 的 variant 给它
we use Virtio 9P to send request, and then we use the standard port to call that to the standard system from front end to back end.
这个地方就是说一下什么是 FUs。
We're talking about what's
file system in user space， 这个其实实现
FUs.
的已经比较久。
It's actually file system in user space. It consists of two parts. One is
一个是那个 Fuse 的 driver，
Fuse driver.
VFS
VFS virtual file system is a common layer in Linux, and the Fuse driver is a kernel space. Another one is LibreFuse.
那用户只需要简单
The user just
实现一个 box 回调，
use libuse,
可以实现一个他们自定义
and they will be able to achieve a customized Fuse
但这个
demo.
地方就说了，就是说，如果我要把这个 Fuse
If we're going to use a Fuse
虚拟化这个环境，
in virtualized
可以用
environment,
虚拟化环境上。
how can we use that in the virtual environment? What kind of changes do we need to make?
那这个地方就是说了，就是 Virtio-fs。
This is about Virtio-fs.
现在也是 Red Hat 的主要的 drive。
It is the major drive of Red Hat. I see in the community there are some Chinese colleagues that are already submitting patches. This is the shared file system that lets virtual machine access a directory tree
这个
on the
这个
host.
地方其实初衷是说，
Actually,
设计的是提供一个
it is
local 的
designed to offer local file system semantics to replace 9P because 9P is still a network file system.
然后目前这个 Virtio-fs
Right now, Virtio-fs was started
然后 spec 现在也没有
and is being developed. It's not finalized yet.
然后现在是 review 的这个过程中，大家如果
Virtio has been submitted to the community. If you have any opinions, you need to raise about your request for new features or new solutions or any other requests that need to be added. Actually, it includes
第一部分是 Linux， 当然是 Linux
four parts. The first one is Linux.
Fuse 的这个 driver 之上加一个 Virtio 的一个传输层。
So you need to add Virtio transfer layer above Linux.
这个
And the second one is QEMU, and then Fuse, and Kata container in 1.7. The modification has already been added.
然后这个地方最重要的一个改进嘛，就是我认为一个最重要的改进。
One of the big improvement here is the DAS.
这个是通过那个在 Virtio 里面那个 spec
It is in Virtio in the spec. It has added a shared bar to be allowed to present a persistent memory, so it will have the bypass the cache.
那这个地方就是说，其实就是说刚刚说的那几个。
So this page is about the projects we have mentioned. They have already realized the open source and Virtio FSD. It is in the QEMU data. There is such a process of Virtio. So if you to evaluate, actually it's already working now. And pass-through, why we call it pass-through, even if it has received a few requests and it didn't have any implementation, it will just pass through to the existing file system via ext4 or XFS. So about the SPDK proposals, the backend are all the same compared to kernel. The only difference, one is at the fuse target. We do not have the fuse. We have we host the user library, so that will. That means that for the Vhost-fs target, we can get the fuse Vhost request, and then we will call the Blobfs API, and then via the blob driver to be put into the physical board. So you can see that that part is kind of end-to-end, and that's part. So far, we do not think there is any proposal which can bypass there.
这个地方就是单独再提一下这个 direct access
about
for
the direct access for sales. It is via the bar memory ready to provide the 4G cache, to provide the kernel space bypass cache.
那我们现在就到那个 SPDK 这个 Blobfs.
So about the SPDK, Blobfs and Blobstore. For the SPDK, Blobfs and Blobstore, the current implementation is very simple. It is mainly for large files. For small files, it is not good enough at this moment. And for application, it is interacts with chunks of data, which is called a blob. So one blob can be consisting of different chunks, and then the apps can do not consume block, just as RockSDB, and then designed for fast media that is a more friendly optimization. And what is more important is the following points. First is the asynchronous there is no blocking, no queuing, and no waiting. It is fully parallel, no locks in I/O paths. So this is about the Blobstore, but for the Blobfs, there will be locks. Then the underlying layer for logic volumes, we have the snapshot and the theme provisioning functions. So this is the layout of the Blobstore. We can see that it is different kind of different kind of pages. For one page, it is for MB. So if you are from LBA0 to LBAN, so the space is one cluster, and cluster 7, 8 is a larger one. So this Blobstore, you can regard it as a array of the pages. And this is the Blobstore. It is stored in pages in the reserved regions of the disk, or where we call it metadata. I'll quickly go through this because these are very details. So this is about the tables. Actually, for views, it is a different kind of requests. And for Blobfs, it is different kinds of APIs. So you can correspond them together. For example, for lookup, if you are going to look up a file, we have a iteration. We can say that it is from the first file to the next file, and then the get tribute, the open release, create, delete, read, write, rename, flash. So these are the common APIs. We have the asynchronous APIs provided for the QEMU compared to VSD. It is totally asynchronous, but the synchronousness have some limitations. It means for the underlines, you do not need to lock, but for the files itself, you need to have the lock. And these are also some details, which is about the views corresponding. We can say that it has been embedded in a WinRing. So for the general field request, it will also put in WinRing. So this is about the open and close operations in Fuse and in SPDK. For example, if on the top it is open, then there will be two requests. One is lookup, the other is open. And for lookup, we will have the BFS to iterate to the file and then open it. So that is kind of preparing resources. For close, it is just the opposite. Like open, it has two. One is release, the other is forget. So that area is related to the SB API. So this is some of the implementation details with read and write, as well as how you embed the data. So we can see that on the bottom it is POSIX read, and then it has been converted into Fuse read, and then to put it into the Fuse in header and Fuse reading. And then for the the fields in header and the fields reading to embed the data into a layer, and then for the vhost target, you can see that if it is different, there will be a new request. Then it will get the fuse request, and then it will call the file read A to process the request. So you can see that this is the fuse read, and then data buffer, and etc. To summarize, as I have already mentioned, the Blobfs currently can only support limited file APIs, and another big limitation is that we can only support append write. And another thing which is not available is DAX is very useful, but if you enable DAX or disable DAX, if you do some evaluation measurements, the performance would be quite different. So that is why for IMAP we didn't quite realize. And then friendly for write, the second point, the workload is very friendly, and we also need to think about some using scenarios. For example, if to use it in containers, whether it is to write is friendly or for read, the read cache feature is very simple. And the third one is the big files. It is not friendly to small files. And the next step plan, we actually, because for file system, it is very complex. There are some limited scenarios. Originally, we want to use the RocksDB, but now user scenarios has been changed, so that means we are not limited to the RockDB. So that is why if we're going to expand to a fuse, we have a lot of work to do, including the existing models. For Blobstore, the underlying layer is totally asynchronous, and there is no lock. But if it is related to the file systems, for example, if you have different requests to process or to control the different files, at this time you need to add the lock. If it is different kind of files, you can put it into parallel. Benchmark for the Vhost-fs itself, it was just realized recently. So our next step plan is we will make it more mature, either to wait until the community is mature or until the Blobfs is mature. Then we will do some benchmark test. Then on the bottom, there are some useful links, because for Tower FS, you can see that from the second link you can get it, and for the SPDK related support, it is on the number 1 and number 3 links. So what you need to do is to prepare the QEMU, the Linux. And the benefit of this is that we only need to pay attention to the timing of the Blobfs. For QEMU kernel and fuse, we just give it to Red Hat or community to do it. So that means we don't need to pay too much to the upstream. And next, about our SPDK community. Currently, we've got a different kind of ways. We have the Slack, which you can find us and then can track some tasks, and then GitHub, Jenkins, and the weekly calls. So anyway, it is a open source program. You are welcome to join. Any questions?
Hello. About DX, I still have some confusion because based on our understanding, for the NV address and block address needs to have a mapping, and then the mapping will be saved to the page table, and then you can access the physical address. But on this chart, I don't see how that does it function. How do you do the mapping? I don't understand it fully. Actually, when you look at what IO, it has the bar space. It doesn't mean that you need to have a physical device. For how do you simulate MDIM? You can use memory. So I can inform my guest. So this part of the memory is persistent, and then it will be bypassed in the memory. Suppose I have 2G. Sorry, I can't find it. Suppose I have 2G data here. I know it. If I have 2G data on the host, because if we have requested DAIE and then send it to the guest, so we have a persistent memory with the 2G data, and it's a device. And then on the volatile DEX, it will be on the hosted memory. So actually, when you have the address, it will bypass that. So it is bypassing this data cache. If you map that, if you have a 2G file space, actually you can see it on the host. Okay, I got it. I have another question about PMDK. I think it's also included in SPDK. PMDK and SPDK are two different things, but normally when we have summit, it's together. I think for the SPDK in the roadmap is included. Our roadmap is saying that we're supporting PMDK. We can call the API, but they're still running their own community. Okay, thank you. I'm still asking about the DEX because you haven't set up about the mapping and unmapping SVPI. Can the block do this? Yes. We still do not support random write. Random write. It's not a random write for the 2G bar memory because you need to map the FD in the QEMU. For your vhost user dimmer, I understand Blobfs can only be accessed by dimmer instead of QEMU. For vhost solutions, actually, QEMU is registering the whole memory on the host because QEMU is an independent thread, and vhost and target is also a thread. Actually, they can have memory sharing. That's why we require huge TBFS. That DAIE is only the guest memory. DEX is in the additional host, and QEMU needs to to change that. It doesn't need to change. It also needs to register on the host. I don't remember that we have such a thing. You can take this part of the memory is reserved by QEMU for 2G space. It will be started together with QEMU. That includes 2G memory. That means for the vhost dinner, you are going to operate this. Yes, we can do that. But the key is that what is the reason for you to use SPDK? So maybe you want to flush after writing the memory. But our backend does not support random write. Even when we support the Blobfs, can only do the flush when we support that, because someone has written on the map already. So it is read-only cache. Yes, we can only have a read-only cache. We can have anyone to update and write directly and update that to the car. If we can achieve that, the DEX can be achieved. If you're doing that, will that be on the vhost daemon, right? Because the memory belongs to QEMU. I still want to ask about DEX. I don't know in the DEX kernel if you used FX. What is the purpose for that? Is it a must? It's optional. And we have also marked that as unstable. If we don't have these backend thing, we will have them DIN card, which is for persistent memory. If you don't have that card, when we have mapped to the DRAM, it can be lost. Actually, it will go directly to peer cache. If you're going to write back and flush, actually, the things in the memory will be flushed to the disk. If you have 2G disk space, which is corresponding to the LB space, so which side is maintaining the table? If you don't have that, it will go to petacache. If you have DEX, the backend block device is persistent. That means it will go directly to the block. But if it's a virtual, it's another story. It will just tell the desk kernel that it is persistent. It will bypass the guest. So ultimately, it will still result in that part of the memory. But actually, for the cached data or cached metadata, maybe you're connecting that with MIT. There's no memory block, so the cache you'll lose. Are you doing that for performance? The purpose is to reduce the bit cache footprint. For this solution, it's also an host memory, and for the guest, it's also host memory. I don't have physical persistent device, so the performance should be the same. But when you have a paper cache, you can have some cache, so you don't need to go to Virtqueue. Normally, if you don't have a DEX device, if you're going to write SSD, actually it's in petacache. When you have this device, it's no longer necessary. But I think the reading performance will be worse because I can access memory, but now we're accessing the disk. When you are accessing it's not as fast as petty cache. When you have a physical disk compared with DRAM, of course the performance will be worse. Because I've seen some tests for Apache desk or non-desk access. Sometimes the performance will be worse. Yes, thank you.